Hello, everyone. It's Anu again, chemical engineering graduate from Georgia Tech, and we're back again with TXY diagrams. So if you haven't watched part one, I'll put a card up here so that you can actually get an intro to what TXY diagrams are. I highly recommend you watch that if you are not familiar with TXY diagrams and don't understand how to read it. I'll do a little bit of a refresher here as well, just so we're all on the same page, but I highly recommend again that you watch that video. So here we have the TXY diagram for an ethanol water mixture, right? So on the x-axis, we have the mole fraction of ethanol. So 0 is pure water and 1 is pure ethanol. On the y-axis, we have the temperature in Kelvin. And then you can see both our bubble curve and dew curve, right? And I don't think I mentioned this quite explicitly in the video previously, but our bubble temperature curve, right, basically tells us, okay, let's say we have a 0.4 composition. The bubble point is that temperature at which you first experience that first bubble of vapor. So below that line, remember, you have pure liquid. This is liquid, this is pure vapor, and everything in the middle is liquid plus vapor. So it's as soon as you hit that curve, that's when you have that first bubble of vapor, which is why we call it the bubble temperature line or the bubble curve. You keep going up, or in this case, we can go down, right? As we go down from the vapor, we hit our dew temperature because this is when you get the first drop of dew, the first drop of liquid. So that's the dew temperature or the dew curve, right? And then, of course, ethanol, water, these are incompatible mixtures. So you can see that they kind of intersect right around there. So that's at around 0.894 and a temperature of 78.15 Kelvin, or not Kelvin, Celsius. I did the conversion and then I kept it in Celsius or in Kelvin. But yeah, 78.15 Celsius. And this is what we call an azeotrope as a reminder, right? So with this, we're able to actually read the diagram, right? So with all of that, what I do want to give you first is something called the lever rule, right? Because knowing the lever rule will actually help us solve a lot of the problems, actually the example problem we're going to do today as well. Um, but here's what the lever rule is basically saying, right? Is so for any given mole fraction, let's say we're at zero point 0.4 and we're at 360 Kelvin, right? And draw this line. And so it intersects the bubble curve and the dew curve at these 2 points respectively. And just remember that we can find the compositions of the liquid and vapor simply by reading off of the graph, right? So we can say that, okay, this one, X ethanol is about, oh, I don't know, or it's around zero point 0.1. So the liquid is about 10% ethanol, whereas the um, vapor is about 45% ethanol, right? But what the lever rule is really telling us here is how much is liquid and how much is vapor. So let's say we had 100 moles total of this water ethanol mixture, right? So we have, 40 moles of ethanol and 60 moles of water, right? How many moles are liquid and how many moles are vapor? And the way we do this is using what's called the lever rule. And so I want you to imagine that at this point, we have a fulcrum, basically. All right, so we have this fulcrum here, right? And I want you to imagine it looks sort of like this, right? Where we have a very little length for the vapor and a really long length for the liquid. So let me ask you this. In order for this to be balanced, which has to be more? or which one has to be heavier? Well, the vapor, right? So the vapor has to be a larger component than the liquid. So much more that it balances out the the weight of the liquid, essentially. So in this case, we have a lot of vapor. To further illustrate this point, let me show you this way. Let's say it's at the very end, the fulcrum's at the very end. And so we have liquid and then vapor. The only way that this can be flat is if there's zero liquid. So this is actually the case of 100% vapor. 100% liquid would look like this, graphically speaking. Right? So this is like when we're on the fulcrum, you basically draw on the bubble temperature line. So the weight of the vapor is essentially zero, and the liquid is full. So that's why it's flat. And then, obviously, if we have it in the middle, this is 50-50, liquid vapor. They both have the same amount to balance each other. And so what the lever rule basically is doing here is we are converting this kind of intuitive seesaw idea, and we're making it quantitative. So I'll just quickly derive this for you so you can actually see this in action, right? So we start with a full balance, a total mole balance, right? So our total mole balance is the total, which we'll call F, is equal to L plus V. Then we do a component mole balance. So we'll do it for ethanol, right? So the ethanol balance is F times Z, which is the overall fraction, times L times X, which is the mole fraction in the liquid, plus V times Y, which is the mole fraction in the vapor. So just by doing a little bit of algebra, we can actually move things around here. I'm going to actually substitute here that L is equal to F minus V, and then plug that in into our ethanol balance. So we get F times Z is equal to F minus V times X plus V times Y. Now we just group terms, move things around. So we get F times Z minus X is equal to V times Y minus X. And then moving F to the other side, we get V over F is equal to Z minus X over Y minus X. And you'll identify that this V over F is actually our vapor fraction. It is the fraction of moles in the vapor. Okay, and so that's the derivation. Likewise, we can actually do the same thing for L over F, and I'll encourage you to do this derivation yourself to figure out what that actually becomes. And you'll see that the liquid fraction will just become, well, 1 minus this, right? So what would that become? That would become y minus c over y minus x. And so now we have a set of equations that we can actually use to find the vapor fraction and the liquid fraction. And find, okay, how much vapor and liquid do we actually have? And we know that this will essentially balance our seesaw that we were talking about earlier. This will balance the seesaw. Okay, so now let's actually do a problem together here. Okay, I have 100 moles of an ethanol water mixture. Overall composition is Z ethanol is equal to 0.30, and the temperature is 82.7 degrees Celsius. So we have a couple of problems we want to solve here. You first want to find phase compositions. Then we want to find the vapor fraction. And then lastly, what we want to find is the number of moles of liquid and vapor. So let's do that together. So if I draw a line around 0.03, and we're going to try to make this as straight as possible here. Okay, and then 82.7 degrees Celsius. Well, in Kelvin, you add 273, so that is 355, roughly speaking. So if I do this, and I go to 355, okay, we can see that actually that's right on the bubble point curve. So that means that this mixture is a saturated liquid. It's right at the edge of the two-phase region. It's just about to start vaporizing. So phase composition is, well, you only really have liquid, and that composition is essentially liquid, and that composition is basically the same. X equals 0.30, and then X water equals 1 minus that, or 0.70. You know what, I'll just write the ethanol one. Is X, the ethanol fraction is 0.3. Now you could also ask, what is the composition of that first bubble of vapor? So we can actually go here, cross the line, and actually read what our composition is and say, okay, that looks to be that our ethanol fraction will be about, I don't know what that'd be. We'll say 0.56 or 55. I think both of those will work. So we're looking at pretty much 100% liquid. And so all 100 moles, not 1,000, 100 moles are basically liquid with maybe one drop of vapor. Great. So that's an easy example. Now let's try this at a little bit of a harder point. So let's actually try this. We'll do this 1 degree hotter. So instead of 82.7, we'll say 84. 84, which becomes 377, roughly speaking. So now let's do the same thing here. We want the fraction, we want phase compositions, and we want the moles of liquid. So instead of 355, we're now operating at I did the math wrong, didn't I? It's not 377 Kelvin, is it? It is 357 Kelvin. My apologies. So we can draw the line cross like this. That's roughly 357. So now we can just read compositions from the lines, like so. So we can say that the liquid is X ethanol equal to, we'll say that's around 0.1, so 10% ethanol. And then the vapor composition, or Y ethanol, that I would say is around 0.47. So about 47% ethanol there. So now let's find the vapor fraction. I don't know what happened to my V there, vapor fraction. So remember, the vapor fraction we computed earlier is V over F equals Z minus X over Y minus X. So we have 0.3 minus 0.1 over 0.47 minus 0.1, which is equal to 0.2 over 0.37, which roughly equates to 54%. So this means that we have about 46 moles liquid, and we have about 54 moles vapor. And that's it. This is how we actually use these TXY diagrams in practice. All right, that's it for today's video. I hope you got some value out of this. Again, if you haven't watched the first one and you were a little confused by this, I highly recommend you watch the first one. I'll show up that card again in the corner. Anyways, I'll see you guys in the next video. Thank you.